Welcome back. In the previous video, we spoke about what binary operations are, and then most especially we spoke about the closure property. And in today's video, we'll be looking at the other properties, most especially the commutative property for this particular video. I realized that the previous video was a very long one, so I'll try my best possible to reduce the time for this video. Now, before we focus on the commutative property in this video, let's do a quick recap of what we did in the previous video. So, a quick recap. We said that for to have a binary operation, right, we should have two elements, right? So there should be two elements from what? A certain non-empty set, and we called that non-empty set omega. And then we said that this omega could be either a set of integers, set of natural numbers, set of real numbers, and so on, what have you. Now, these two elements from this set, and then the operation, you can use star, triangle, you can use anything to represent the operation. Now this operation should be defined, right? Should be defined on this element, so on the two elements, on the elements from, so elements from what? Omega. Bear in mind, omega could be any of these sets, right? Or any defined set you choose. Now, so if you have this operation defined on this element, then another thing is, once it takes this element, right, from this omega, what happens then? So it should, when operating on maybe the two elements, right, which are from omega, for all a, b in omega, right, it should provide a certain answer. So let's say it should provide c, and then this c should also be what? In omega, right? Let's keep that in mind. So basically this was what we spoke about yesterday, and then we said that the definition, right, the definition could vary. The well-known binary operations that we know is the addition, the subtraction, the multiplication, the division, and the others, and what have you. Now, we'll be using these, the well-known ones are the ones we are going to build on to get the more generalized ones for these videos and then the subsequent videos. Also, we spoke about the closure, and then we said that for closure, if our omega is closed under the operation under maybe the binary operation star, it means that whenever you take any two elements from omega, so any two elements ab from omega, and then you operate on this element, the answer that you get should also be part of omega, which is to tell us that it's not all binary operations that we'll find out that are closed. And then in the previous video, we showed some examples using a table, but then we realized that all the examples we saw were closed. So before we continue, let's look at a particular example under the closure that is not closed. So for instance, if we should consider that, so consider that what so today I'm using this operation is defined, right, on this set. So here our omega is for 2, 4, 6, 8, right? Now if this is the omega and then this operation is defined on this set as, so if you have two elements, let's say xy, remember we said that the operation is a function, so you have that should be equal to x operation y, and then we are saying that the definition of the operation is that whenever you see x operation y, add the second element to the first element and then subtract their product. So this is the definition of that element. Now, so let's see if, so from this question we are to show that what, that omega is not closed, right? Not closed under the operation, right? Now how do we show? We said that if it is closed, then all the operation with all the its elements should belong to what? Omega, right? So for our solution, all we have to do is just look for one element that will disobey that property of closure. Bear in mind, we said closure, if you should take any element and then you operate on those elements, right, their answer should also be found in the set. So now let's see. So now let's taking, right, sorry, our x to be 2 and then our y to be what, let's say 4. Okay, now if we should operate 2 operation 4, by the definition should be 2 plus 4 minus 2 times 4, right, which gives us what? This 2 plus 4 is 6, 2 times 4 is 8, so this should give us a negative what? 2. Now negative 2 is our answer here, but negative 2 is not in what? Negative 2 is not in omega, right? Because when you look at the set omega, realize that the omega is 2, 4, 6, 8, and negative 2 is not found in omega, which implies that since our answer is not found in omega, so since what, 2 operation 4 is not found in omega, right, we say that what, the operation, right, is not what, closed. It's not closed, right? Hey, sorry, the omega, our set omega is not closed under what? The operation star. So basically that's what we, so in this video realize that the operation is not closed, right? The set is not closed because our final answer here is not found in our given set omega. Alright, so just for the quick recap, now in this video we'll focus more on another property, and this property is called the commutative, right? Commutative property. Okay, so now before we start with the commutative property, let's do a quick recap. Now we said that the well-known operations, binary operations, are the addition, right, the multiplication. Now look at, for addition, we know that a plus b is also the same as b plus a, is that not it? Or to be more specific, let's say 2 plus 3 is the same as what? 3 plus 2. which will obviously give us the answer 5. Is that not it? And then let's look at A times B. And we say that A times is also the same as B times A, right? Which is also equal to what? So let's say 2 times 3, which is the same as 3 times 2. And obviously that will give us 6. Now, this property of addition and multiplication, right, is called the commutative property. So as we said that what? The well-known binary operation, the well-known ones that are properly defined, we have the addition and then the multiplication and the subtraction and the others. But then amongst those, I think we have addition and then the multiplication being commutative. I think the union, intersection are also commutative as well, and there are a whole lot of others. But then we are going to just pay attention or focus on these two for now. So since these are the known ones, we want to see how we can generalize this idea to any other operation, star, triangle, or any other operation, what have you, right? So let's see how well we can do that. Now, so by definition, right? So let's go to a definition. By definition, we say that what? A binary operation, right? A binary operation star. So star is what? Okay, so a binary operation star, which is defined. Bear in mind, the operation has to be defined on a given set. And what do you mean by the definition? Being told that A star B is equal to maybe 2A plus B. That's the definition. And then for the addition multiplication ones, they have already been well defined, so we know how it's done. Okay, so it was well defined on an empty set, right? So on a non-empty set, and here we are using omega to denote our non-empty set, right? And we said that this omega could mean the set of integers, natural numbers, real numbers, and a whole lot more. Okay, now, so a binary operation star defined on a non-empty set, right, omega, is said to be commutative. If so, let's say x, right? So for any value x, operation y, right, is the same as y operation x for all values. So for all values x, y in what? In omega. Alright, so basically this is what the definition of the commutative property means. So we first have to check and see whether x operation y is the same as y operation x. Then if x operation y is the same as y operation x, then we can say that what the operation is commutative. Okay, so now let's try and see some example. Alright, now the first example, we are going to take a more generalized one. Okay, so given that, let's say x star y operation y, always remember that x operation y is defined as x plus y plus xy, right? We have to show that star commutes, right? So star is commutative. So let's see. Now we said from the definition that for it to commute, x star y should be equal to y star x. Alright, so we already be given that x operation y is equal to x plus y plus xy. Now we are now supposed to, and then so what will y operation x be? So y operation x, right, is the same as what? Wherever you see, so y is now coming first, so which means that this will now become y plus what? X plus what? Yx. Exactly. Now looking back here for the addition and then multiplication, we said we agreed, right? Or I told you, if you don't know, that addition and multiplication are already commutative, and then from this definition you can see that we are adding and then multiplying elements here, adding and then multiplying elements here. Okay, so if that's the case, then we could say that the x plus y is the same as y plus x, which is here a plus b is the same as b plus a, right? So here we can say that since what? Addition is commutative, right? It's commutative. And what? Sorry. And multiplication is also commutative, right? Commutative. Then it implies that x star y, which is equal to x plus y plus xy is also equal to what? Y plus x plus what? Yx, which is equal to y star x. So what we are saying is that x star y, its definition is x plus y plus xy, right? And then y star x, its definition is y plus x plus yx. But since addition and multiplication are all what? Commutative, it means that x star y, right, is equal to what? Okay, let me make sure the colors are consistent here. So we have, it means that what? X star y is equal to what? Is equal to y star x. And hence we can now conclude that the operation star, right, is what? Commutative. So basically that's how we show, or that this is a more general way of showing that a given binary operation is commutative, right? Now let's look at another example. So example 2 here. Let's look at a different scenario where, so now for a second example, let's say we have operation, so x operation y, right, to be equal to what? X minus y plus xy. We are trying to use the general one so we could properly understand the concept. So once you understand the concept, then we solve examples using numbers and then hopefully to stick. So now for this particular example, what do we do? So it's the same thing for x and y to commute. So here in this particular one I will go a little faster. For this to commute, we say that x operation y should be equal to y operation x, which implies that what? We are told that x minus y plus xy, this is for sorry, this is for x operation y. So now let's look for y operation x, right? Now y operation x is what? It's going to be y minus x plus what? Yx. Now a quick note is, even though addition x plus a plus y, a plus b is equal to b plus a. Now the question is a minus b the same as b minus a? No, because if you have 2 minus 3, this is not the same as 3 minus 2, as this will give us what? -1, and this gives us what? 1. Obviously, so here we say that subtraction is what? Not commutative. Okay, so here, because we have a subtraction here, and then obviously this could give us a different number or a different value from the addition that we have here. Sorry, the subtraction that we have here. It means that our y operation x is not the same as our x row. Let's put it in writing. So since what? Subtraction is not commutative, right? It's not commutative. It means that what? X operation y is not okay, which is equal to the definition, which is equal to x minus y plus xy, is not the same, is not equal to what? It's not equal to y minus x plus what? Yx, right? Which in the long run is not equal to y operation x. So here we can conclude that what? X operation y is not equal to y operation x. And since this is the case, then we say that what? The operation is not commutative. Commutative, right? In the so yes, the operation does not commute, or the set is not commutative under the operation. So basically that's that. So that's basically it. So now we've concluded that our given operation, the defined one, is not commutative. So that's another way to find out for the general one. So now let's look at a more specific example. I know that I said this would be shorter, but just bear with me. Now, so for a more specific example, let's just look at this. So we'll be going through this really fast. So we have 3 operation 5, right? Still using the definition, okay? So before then, let's use the definition. This very quick one. We have, let's say, x operation y to be given as well. Let's say x minus y plus xy, right? And then we have to show that using this definition, right? So using this definition, we should show that 3 operation 5 is commutative, or we have to find out, is this commutative? That's the question. Is it commutative? So now let's see whether it's commutative or not. So we said that if it is commutative, then this should be equal to 5 operation 3, right? So now so let's find 3 operation 5. 3 operation 5 will be given as what? 3 minus 5, right? Plus what? 3 times 5. Okay. Now, so this gives us what? Here is -2, right? Plus what? 3 times 5 becomes what? 15. Okay. So -2 plus 15, we have what? That's 13, right? Okay. Our first one. Then let's see for our second one. We have 5 operation 3. So 5 operation 3, we have 5 minus 3 here, plus what? 5 times 3 here. Now, as you said in this side, you realize that, okay, Here the 3 minus 5 we have negative 2, but look at here 5 minus 3 we have 2 here plus what? 5 times 3, that's 15, right? So this gives us what? 17. Affirmative. It's obvious. You could see that 13 is not equal to 17, right? So it says, so here 3 question 5 is not equal to, which is equal to 13, is not equal to what? 17, which came from what? 5 operation 3. So here we can conclude that this implies that 3 operation 5 is not the same as 5 operation 3. And since 3 operation 5 is not the same as 5 operation 3, then we say the operation, right? The operation triangle is not commutative. As easy as that. So yes, so in this video we recapped on what binary operations are, and then the closure property, what it actually meant. We solved another example on the closure property to really know when it's not closed, and then we move ahead and spoke about the commutativity property, and then what it actually meant for an operation to be commutative. Now, and then we solve some examples, 2 general ones and then 1 specific one. So I would be very happy to see if you could use the same definition from the first one. So here I'm giving you a small assignment here. So use the same definition. Sorry for my preferred line. So let's say x star y, right, should be equal to x plus y plus xy. Using this definition, find out whether x star 3 star 5 commutes, right? Sorry. Okay. And then try and leave your answer in the comment section below. And then we'll see you in the next video. In the next video, we will talk more about the other properties. So the next video, we'll be talking about the associative property for binary operations. So stay tuned, and then we'll see you in the next video. Thank you.